Okay, calculus class, how are you? This is going to be a repeat of what I did in period 2. So this is mainly for period 1. However, I have 1, 2, 3 kids, those student council hoodlums, who missed class today to write their tests, which means that you're interested in this too. So, somewhere I gave you a package full of photocopied lessons that we've used in the past and we can use now as well. Please find Calculus Unit 2. All of these are lessons that I've been using for years and years and years and years and years. They're lovely. We're going to need to be careful, however, when we get to something like this. What that is it's quoting homework from a yellow textbook that you don't have. It is listed under course materials, I think, in the LMS. If not, I'll activate it so it is there. But again, I'm going to give you new homework based on this textbook, and we will move from there. But hey, there you go. Okay, so back to what we're talking about here. So you're going to look through that. None of these are numbered. I haven't ever bothered to number this booklet. We're going to go here to lesson 1 on derivatives, and we're going to fill this out, and you're going to add it to your notes, and it is basically going to cover all of 2.2 in, again, this book, and we'll go from there. Lesson 1, derivative rules. The act of using the derivative function on a function, f of x, to create a new function, f prime of x, is called differentiation. Okay, already, I've been using this for years and years and years and years and years, and this doesn't make sense. The act of using the distributive function. You don't use a distributive function. The act of finding the derivative function of a function f of x will create the new function f prime. And the act is called differentiation. Okay? The act of finding the derivative function of a function f of x will create a new function. Creating the new function, there you go. Creating the new function f prime of x is called differentiation. Yeah, so there you go. The derivative function is given by, okay, so as we discussed in class, we know that slopes of tangents are given by the limit as h approaches 0 of f of x plus h minus f of x over h. That is the slope of a tangent to the function f of x. We call that, when we want to talk mathematically, as the derivative function is the limit of h approaches 0 of f of x plus h minus f of x over h. And the function that we're taking this limit of the difference quotient, was f of x. So you've got a function f of x, and we're going to mathematically determine a new function, f prime of x, f prime of x. The function's name is f. The variable that we're talking about is x, okay? So if I had a new function, say g, and its variable was y, then what we could do is find the derivative of g in terms of the variable y. Now, we're not going to do that right now, but we're just talking about notation. Okay, so go back to where I was. So far, we've been talking about slopes of the tangent, which we now know can be called the derivative of a current function f of x, and that is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So, if I want a graphical interpretation of what this is, it's called the slope of a tangent. So if I have a curve, la 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 la, and that would be the slope of the tangent at a particular point. If I had a function that could give me all the different slopes of the tangent, no matter where I went along the x value, then that would be called my derivative function. and I would plug in a particular value of x, maybe here, and it would give me that slope of the tangent at that point. Maybe I can make that look a little bit nicer. Let's say I had this, and I wanted to know the absolute slope of the tangent at this point. And if this was the value x, what I would do, if this was my original function f, I would do all the work. I would do all of this algebra. Notice I would have to know what f of x is. That would give me, so this means this. The act of doing this is called to differentiate. That's an action word. Okay, differentiation. So the act of differentiating, yes, I played with the focus button. There we go, life will get better. So the act of taking this limit is called differentiation, and it gives you what's called the derivative function. And if my original function is called f of x, then this is f prime of x, or the derivative of f of x. All right, I think that's good. So we're going to talk about this act of going through the differentiation in a mathematical point of reference. So the derivative function is given by this. The derivative function, these values, are also the slopes of the tangent to a curve, f of x. We know that. That was all chapter 2. So this is all chapter 1, everything that we were doing. And this new derivative function is also chapter 1. However, computing derivatives from the definition, that's what this is. We call this the definition, or we call this first principles. From the definition is tedious and time-consuming. We will now develop some derivative rules that will simplify the process of differentiation, a mathematical process. Okay, now this is math speak. The derivative of a constant function rule. If f of x is k, so f of x equals k, where k is a constant and k is an element of the real numbers. So it can be any real number at all, which includes every number that you know about except complex numbers. And that is a negative under a square root. So as long as I don't get a negative under a square root, I'm good to go with this rule. So if f of x is a constant, then f prime, the derivative of f, is 0. So no matter what constant I have, the derivative of a constant is 0. I want a proof, and I want to prove this both graphically and algebraically. All right, here's a graphical proof. Let's first consider if f of x equals a constant, then that's going to be a horizontal line. When graphed. And we're all going to assume that we're graphing on a Cartesian plane, okay? So as long as it's graphed on a Cartesian plane, then this is going to be a horizontal line. So that means that, chance to dry. Let's draw this horizontal line. Now, do you want it above the x-axis? Do you want it below the x-axis? I don't know. I'm going to put above the x-axis. Why? Because it looks pretty. So this is f of x equaling some value k. All right, horizontal line. Have you noticed something about horizontal lines? There's something about their slope. Notice for a horizontal line, that rise over run, there's an awful lot of run and there's no rise at all. The slope of a horizontal line is 0. And we know that from grade 9, this rise over run idea. Okay, that's a graphical proof. It shows a graph, it shows a picture, and I think for all of us is a valid argument. Let's do an algebraic argument. Now, if f of x equals k, where k is a constant. Well, the derivative, by definition, is given as the limit, as h approaches 0, of f of x plus h minus f of x over h. Well, in this particular case, recall, f of x equals k. What do you think f of x plus h will equal? So if that's x, go a little bit farther. What's the range value? It's still k. No matter where I am, the range value is k. So therefore, you're going to get the limit as h approaches 0 of k minus k over 0. Oop, big mistake, big mistake. Error, Will Robinson. That's not over 0. That's over h. Big difference, kids. K subtract k is 0. H is never, ever, ever equal to 0. It's getting smaller and smaller and smaller and smaller. Do not make the mistake of thinking that this is indeterminate. It is not. The top is 0. The bottom is some small, small, small number, which means it equals 0. So the derivative is equal to 0, which equals the slope of the tangent, which means that we have proven that if f of x equals a constant, then the derivative of the constant will always be 0, no matter what the constant is. So I've got some examples. If f of x equals 25, then find f prime of x. Now, regardless of the answer, there's another way to write this question. And it looks like this. And what this says is the exact same as up there. The function's 25. Find the derivative of it in terms of the variable x. So this one statement equals the same as this entire statement. Now, what is the derivative of a constant? The derivative of the constant is simply 0. So what is f prime? 0. And again, this is just notation. Over here. We'll talk about this. If this is bothering you, good. That's okay. Let it bother you for a little bit. Let's finish what we're working on and see where we end up. This is pi. This is negative pi. It is a constant. It has a place on the real number line. It is fine for this rule. It is a real number. It's somewhere between -4 and -3. It is a constant. Therefore, the derivative of this puppy is 0. Yeah, that probably bothers some of you, but I could actually graph this. If I went down to -4, if I went down to -3, somewhere at -3.14 is this lovely little line that is y equals -pi. And it has a slope of 0. There you go. All right, let's flip over and keep going. Oh, not lesson 2. I've lost a page or two. Not that one. There we go. Okay. So now, you know what? To break up these videos so they're not too long, I'm going to stop here and I'll come back and I'll do the derivative of a power rule.